Hi, Professor Lee here. In this lecture, we're going to continue our discussion on software engineering. The first topic we're going to look at is testing. In our previous lecture, we talked about various different kinds of development models, including Agile. And one of the key things that Agile needs is testing. In Agile testing, we can look at this chart here. There are various different kinds of tests. There are 4 quadrants in this chart. So the top quadrants are business-facing tests, and the bottom ones are technology-facing. On the left, those tests are more of internal tests to support programming. And on the right, those are the tests that are basically to test at the product level and verify the project or product as a whole. Now, one of the key things we want from tests is fast feedback. Why is that good? Imagine if you test only after the software is running in production, you find something wrong and you go back and fix. And that is a very long feedback loop. And so that will be inefficient. And it's not going to have a good customer experience because now your customer is exposed to the bugs. So we want to find out the problems with the software as soon as possible. So if you look at the bottom left quadrant, where we have unit tests, component tests, and system tests, those tests can be automated. Typically, we want them to be automated. While we're writing a code, we want to have those tests as part of our development efforts. Then we'll move on to the automated tests for functional acceptance tests, where you have a feature implemented, and then it can be verified in an environment where the software is running. It's off of your computer. And once we have the feature is done as let's say we're going back to our Scrum process, in a sprint, in the end, you're going to have maybe a showcase. You show to the product owner or any other stakeholders that might be interested in this deliverable. And you may also have people doing usability testing and exploratory testing. Those are the things to test from the user's perspective to see if the software is easy to use and there's any usability issues. Some of those things cannot be easily automated. So a lot of those category of tests are done manually. And then there are other aspects of tests that we typically also want to perform, including security scans, making sure that doesn't have vulnerabilities. Also want to test maybe the software is it's available in case of a regional failure. If your software is running in multiple data centers, if one of them is down, you want to make sure your software still functions. So that is a summary of the various different kinds of tests here. So the test needs to be performed in a continuous fashion. We'll get to a little bit more details how that's done. And the test suites are automated. Now, test suite is basically a set of tests that are related. And one of the practice in extreme programming, for example, is called test-driven development. Basically, you write your tests, then you write the code to pass the tests. And that's one of the ways to develop certain kinds of modules. And then the acceptance test, as we just mentioned, that is basically for the product owner or somebody that's a customer representative to check the software, making sure it's meeting the requirements. Now, put this in a different fashion in a pyramid. There are the tests, at the bottom is the unit test. Unit test is the closest to your code. When you write a class or a function, you need to have the corresponding unit tests to cover the various different use cases. making sure that the specification of your module is well validated with tests. Now, unit tests at the bottom of this pyramid, they run very fast, and they are also very isolated into your specific small unit of code. And then in the middle, you have the service tests. Now, service tests basically is the test that tests your one component that is called a service. Is a logical component that performs a certain function. And that service tests is gonna run a little slower because now you have to go through maybe a network to verify the functionality. And then at the top of the pyramid is the UI testing, where you're simulating a user, and you would have in an automated fashion, just simulate the actions that a user would take, and then you test that way. And that is obviously even slower because now you may be driving a web browser, or maybe you're driving some kind of a mobile application component. And so at that UI testing level, obviously is more integrated with, maybe it's invoking multiple services. And then, at the very top actually is the exploratory testing, where you're just trying to figure out, we use your judgment to see if you can find any issues by playing around, not randomly. You have some kind of plan, but some of those things are going to be very difficult to automate, so they would be done manually, or to automate it is not economical. Now, let's look at an example deployment pipeline. What's a deployment pipeline? Essentially, a deployment pipeline is it's a sequence of steps that is automated to get your code, pushed into your various different environments in different stages, and then get them verified with the tests, and then potentially just go to a production environment directly. And so this is just an example. There's obviously different ways to do it. By the way, this chart that you're looking at is actually, it's called a sequence diagram in UML. So we'll get to see some of those a little more in the future. So those square boxes are, the components or maybe objects or, different classes. In this case, it would be, on this vertical line here is like it's lifeline, and those boxes, the square boxes on the line, when you have an arrow that points to it, means this is getting executed within this component for that amount of duration. So, for example, the development team checking the code into some kind of version control system, like for example, GitHub, and then automatically some trigger will be executed to run certain kind of tests. Maybe as the unit tests, they will be run automatically. And then, this red here indicates, oh, okay, something failed. It provides a feedback to the developer, and then they got to fix the code and do it, and then do another check-in. And let's say the second time it passes, right? Okay, so that passed, great. And then we'll move on to the next stage. And the next stage, perhaps the application is deployed to a environment where it runs on some kind of server. And then there's a set of acceptance tests will be run automatically, automated. And let's say this time something went wrong. It's probably some kind of higher level logical error. So that failed, and there's another feedback back to the developer. And developer goes in and fix it. Now this goes green. Okay, then you would move on to the next stage. And this may be going on to a staging area. And perhaps it will wait for a manual approval for someone, which is optional. If maybe you want somebody to look at, okay, maybe I want to do some more additional verifications. This is the case here. Okay, maybe as a QA person, which is the quality engineer or quality assurance engineer. that's going to actually check that, make sure that it's not missing anything. Just some additional layer of verification. Perhaps it's some kind of manual verification because automated things already run. It may involve more flow, more systems. And then let's say he, or she verified and is working fine, then approves it. So now the software just goes to production, is released. And so this is a typical deployment pipeline where you see tests performing at different stages. Now let's take a look at architecture. So when we design software, it usually has to come from, what is the approach? What is, you have a business problem, how do you solve it? And there are various different ways of designing software, and when it comes to architecture, how you're building, in the real estate sense, how do you build a house, right? And then, what is the style and look, how many stories you're going to build. So similarly, in software architecture, you may think about in terms of layers, okay? In this case, here is a classical architecture. It's been around for a long time, since 1960s. And you have a client layer. The clients are run, perhaps it's a mobile app on Android and iPhone, perhaps from a desktop computer, and the request goes through the internet. Optionally, it may be loading some content from a CDN. A CDN is a content delivery network. Content delivery network is sort of like a cache mechanism to help you load your static content quickly, like the images of a app or website, and or your JavaScript files and stuff like that. And it would load from your CDN servers that are very close to you wherever you are in the world. And because your actual servers, they're running critical services, may perhaps only in a few locations, you not necessarily running all around the world, but you can have a cheaper solution is to have those caching servers around the world, and then you can load your application very fast. And that's what the CDN is for. So we're not getting into more details here. And then so once you send the request and it goes to, let's say, a load balancer, which is a typical component where you are distributing the request from, if you're a very popular application, you may get 1 million requests at the same time. Think of Netflix. And so you have a load balancer that's distributing all these requests into multiple servers. That's the way you can scale your computing power. And so you behind the scene, behind a load balancer, or then maybe just more than one sometimes, you distribute your load into many different servers. That's kind of their concept here. It's just for scalability. And that server may also have its own cache. Obviously, that cache is for the data access layer. It does not need to ask the database all the time. So obviously, there's different kind of data storage solutions. SQL is just one way. Structured database. There's NoSQL. There's different kinds of database that you may use for your particular domain problem. And so this is fairly, straightforward. A lot of the applications nowadays are you have a client application running in their client devices. They didn't do a whole lot of computing except, rendering the UI. And then a lot of the business logic goes to the server, which may be running in a cloud, maybe a public cloud like AWS or Google Cloud, or maybe a corporation's own private cloud in their own data centers. So that's a client server architecture. Now, what are the examples, right? Well, think of email servers, right? You have your email client checking your emails, and then you have your email servers that stores all the emails and handles the email exchange. And similarly, file servers, right? And DNS servers for domain name resolution. So those are some examples of a client server architecture applications. Now, next one is service-oriented architecture, or called SOA. SOA became popular in the aughts, in the 2000s. And this is an architecture that had a lot of, what can I say, like confusion. And the industry wanted something better to, here is, what's kind of indicating here is that you're seeing one layer of a server. These are kind of parallel, they do the same thing, and you have an application running there. And that application typically is called monolithic application. That monolithic application, it does everything you need to do for this particular product in a single package, and that package gets tested, deployed, and which can be huge. And there's a lot of functionality that's implemented in it. For example, thinking of this Zoom video that we're on, and it handles audio streaming, screen sharing, and a video, and some other, like a chat. And it may also handle, your user settings, your account management, and the payments, right? There's many different areas you want this product to do. In a monolithic application, you kind of just have one application that does everything. And the industry quickly figured out that doesn't scale very well. There's a problem. It's pretty brittle, fragile. So can we do better? So let's, they say, well, why don't we break this huge application into multiple, smaller applications, smaller services. Here we'll call them web services. And you put these services in a repository, and they can be discovered, maybe through some discovery servers, or simply, the clients just, they obtained that service address offline or some other mechanism and have that hard-coded. That's a possibility too. So that discovery mechanism is optional. And all of these services, each of them has its own capability. And then, on the client side, you have your different clients that are called service requesters. Now, this may be a client application, or maybe just a different service that needs to invoke another service. So those clients use its own, some kind of has a controller component that helps the application, the client, to pick the right web service to use that's over the internet. So that's kind of the basic concept from a very high level. And then what are some of the characteristics of SOA? And SOA, as we just talked about, those services are business aligned. And so each service performs some kind of business function. Maybe it handles a payment. Maybe it handles billing. Maybe it handles login, authentication. And then those services are highly cohesive in the sense that, this term is actually what you heard about OOD design. If you design a class, you want your, related functionality in a one class, one object, one module. It's similar here, except this is a larger at a process level, that you have related things, like your payment related things together. Or maybe you have a invoice related things together as another service. So, and then they're loosely coupled, just like a good class design, object-oriented class design. You want to have them loosely coupled because, basically the elements within a class, or in this case, within a web service, they're related. And then the elements in different web services, they are less related, so they're loosely coupled. And they use standard protocols to communicate. For the service to interoperate, they need to understand how to talk with each other. So they use standard protocols. And typically we have a layered approach. Here you kind of see, well, the client server is it's a basic 2-layer, right? But then in a typical SOA architecture, you have multiple layers on the server side. You may have a foundational messaging layer that how your service may communicate through messaging mechanism. You may have some kind of middleware or platform component. You may have a top presentation layer that is handling more of the request handling that's coming in. You may apply certain, things to it, like a check-in for security, like authentication, making sure this has a valid session. There's a very many different approach to this, depends on your particular domain. And then the last, not the least, bullet point I want to mention is they call it enterprise integration patterns. SOA was invented to also solve many of the integration problems a company faces. A company goes through its own life cycle. It may accumulate different kind of software over the years, through mergers, acquisitions. And then the systems it has does not work well together. So there needs to be a way to integrate them so to bring them to useful life and to serve a purpose that's meaningful. So enterprise integration patterns is a sort of a pattern that's going to help engineers design solutions, how to solve those enterprise issues when it comes to integration. So we're not getting into details here, but there's references in the back that you can read more about. And here is just another point of view of what we just talked about in a little more detail technically. This is a SOA architecture that it's from a standard made by W3C. And this standard uses XML as the main data exchange format. As you see here, there's a discovery agencies, that's the service registry, how you discover what services are available, right? So this is actually an optional component. You may discover it automatically, or you just statically just encode, put your URL or whatever other parameters you need into your code. But then the primary thing really is just between the service requester and the service provider, and they interact with each other. It's the client service model essentially. And except this client is talking with one single service, and then you have a multiple service in the back. And that interaction is also standardized. It's called a SOAP message. SOAP stands for, I believe, the Simple Object Access Protocol. And this is, if you look at the name of the XML elements, it looks like an envelope it's like a letter. Essentially, that's it's encoding a particular message here. What it's trying to do is to say, get me the stock price for a stock ticker symbol of T, which is AT&T. And the top portion of this request is actually just says this is an HTTP request of version 1.1. You're doing a post to this URL on this particular domain. And the content type is a XML message encoded in SOAP standard. And that is basically what it is. And this was a popular also, but then later on, people realize, XML is very verbose. If you look at all of this, really the meaningful thing is, say, I want to get the stock price, and then the stock name is T. I mean, there's a lot of other tags and letters. So it's just kind of a little bloated. Have too much data to transmit over the wire. It's a bandwidth issue. So there's a lot of criticism. That's one of them. And so people ask, how can we do better? Yes. So essentially in the last decade, 2010 and beyond, and a new architecture style called microservices emerged. And now to illustrate why this is important, what is trying to solve, right? So we're comparing here with a monolithic application. And so, in a monolithic application, you put all your functionality in a single process. You see these different shapes of functionality. They're all together in a single package. And you get that thing deployed to a beefy server, essentially. And you want to handle more requests. And you basically, you scale that whole server, by either adding more hardware to that server, or you, do a load balancing with in the previous diagram you saw to scale that out to multiple servers. Now, a microservice pattern, it sounds a little similar to what we just talked about of the SOA, but there will be differences as you see. So in a microservice architecture, you put each element of this functionality, you put that into its own separate service. And in microservice, micro means small. And how small, that is a judgment call. If we have a specific example, perhaps we can talk about what makes sense. And in fact, the size of the microservice can evolve. And at some point it feels too big, you break that down into logical, separate services again. And that's a possibility. So, or you have a bunch of small services, really tiny, small. They started small, they remain small for some reason, did not grow into the size that we expected. Then you perhaps even combine some of the services, so they can evolve over time. And so the way to scale your new system, where you broke that monolithic application into multiple separate small services, microservices. And so this is one way to do this in the same machine, where you may be running still all those functionality. Previously was in a single package, single process running on the server. Now that same server, you still share the same power. You may run this now different microservices as multiple processes on that single server. Then you scale your servers that way. So as you see, it's just a different way of arranging. You're putting your different functionality that's in the same service. Now you put in that into multiple server processes. Each have their own, and we'll see. There's some advantages of doing that. And now when we talk about microservices, we also have to talk about the processes, the people that actually make them. And in this diagram, there's actually, this is an illustration of a Conway's law. What is Conway's law? Conway's law says any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. If you have 3 teams, each of them are specialists. You have UI specialists, middleware specialists, and database specialists. Then the software you produce with these separate teams are going to be like this. You have a UI component, you have a middleware component produced by the middleware specialist, and then you have a database component produced by the DBAs. And so what's the problem here? Well, the main problem is that the teams are siloed. It is the communication between the teams, the cost is high. If UI makes a change to, their design documentation, or the code that changes to something, but then they need to communicate with the middleware specialists and go through a whole planning cycle to incorporate that change. It can be very slow and inefficient. And that back and forth between the teams, it's just inefficient. And nobody kind of feels responsible if something goes wrong. And so accommodating change is hard. And we know this is not really necessarily the desired team formation, as we saw what we wanted, like say if we're adopting Scrum methodology. But again, we'll get to look at this, how it evolves. So a better way to organize your teams is to have cross-functional teams. In each team, you have people that can do different things. Essentially, if you're making an application, you want all the people that can do UI, middleware, a database all together, so you can make a complete application independently of other teams. So now your communication cost is much lower within your own team, and you meet every day, you collaborate very closely, and so that is just more efficient to work that way. And so now you have different teams that are more or less parallel. They can all do the same things essentially, and then they each are responsible for a different part of the application. Let's say they have a checkmark service. You have, this looks like a cashier, say a cashier service, and then you have a diamond service or a Ruby service. So you're organizing your teams around the capabilities, and they are more or less parallel instead of organizing by functions. So it's called cross-functional teams. So this is a better improvement. And then, so you have this cross-functional teams. In the monolithic world, they are making one app. And this one app does checkmarks, rubies, and cashews. And then they also handle the database where each of them needs to be stored with a state in database, and you manipulate your data. In a microservice architecture, what you do now, you separate them out into different services. Each of them, own its own database, and they don't share its own database with other services. Now, if this cashier service needs to access the checkmark data, it has to go through its public interface, which is the APIs, not by talking to the database directly. This is encapsulation, data encapsulation, just like the principle with OOD, where you design your data is hidden from the outside world. You organize your data in, you can evolve your data organization or structure as you see fit. It's similar to here, although it's just at a larger scale for an application. And here, this actually part shows just you have multiple servers that talk into the database, but this is one application. Now, so we go from the monolithic application, you're scaling your application with multiple servers, but each server you have a single process where it does all the functionality. And versus in microservices, you have different each functionality or business capability is done in a separate process, a separate application, separate package, and then they are running its own server, or they could be sharing same server as well. But this is just conceptually, you see the difference here. And then you have a UI component. Now in the monolithic world, UI is in every one of those. So as you have everything is all together. Now this allows you to scale your each portion of the application independently of other pieces of your application. In an application, some functionality are used more than others. You have more traffic for certain things. Maybe your checkmark is used most heavily. Well, in this case, what illustrates here is indicating your Ruby service is used more heavily. So now you need 2 servers to scale. But you don't need to have 2 servers for cashews and the checkmarks. So it gives that flexibility. You can more efficiently utilize your computing resources and without waste. Here, in order to scale your Ruby, now all the other pieces also get to scale down, although they're not going to be used as much as a waste. All right, next we're going to look into DevOps. So DevOps is a kind of a buzzword nowadays, but it is okay. What is DevOps, right? Behind all the hype. Now, DevOps is the combination. This is according to AWS. DevOps is the combination of cultural philosophies, practices, and tools that increases an organization's ability to deliver applications and services at high velocity, evolving and improving products at a faster pace than organizations using traditional software development and infrastructure management processes. So that's a pretty good definition. You know, a couple of key things you're taking from that definition essentially is it's basically a set of philosophies, practices, and tools, and they are designed to increase the organization's essentially agility, ability to deliver applications at a high speed or high velocity. So that's what this is about. Of course, a company that can do that efficiently is going to be more competitive. So it can be your competitive advantage. And now back to this, we look at DevOps is, you know, the organization needs to cultivate a culture. The dev and operations, developers, operations, traditionally they are separated. I mean, they're separated in different buildings, or maybe, you know, very far away, many miles away. So that's kind of how it was done traditionally. And then they say, well, no, this is not good. This is not efficient. And, you know, developer made an application. Now it takes weeks or a month to get a release out. So now we say, well, let's share this responsibility of developing software and getting this up and running, you know, released to the customers. So, so DevOps is promoting, you know, faster feedback, closer collaboration, right? You want to build your quality in through rigorous, you know, automated testing at various different parts of your deployment pipeline. And then you want to automate, you know, you don't want to do a lot of manual things. If you do manual things, it's slow, fragile, you cannot keep up. And some organizations deploy, you know, thousands of times a day. And how do you do that? Automation. So the culture at the organization level is, let's not have silos. Silos are not good for efficiency. So we want the teams to be autonomous. You know, they sort of self-organize. They get the things they need. You know, in each team is cross-functional. They can do everything they need. They're empowered. So there are many different characteristics that describe what DevOps is. To just look at take a closer look. It is a kind of combination of what we discussed so far. And first is it promotes agile practices, the things that we talked about before. That, for example, Scrum process is one of the agile methodologies. That's something that, you know, it advocates. We also want to use microservices. It's better than the monolithic applications. Yeah, that allows you to adapt and develop your applications fast. You know, when you change one thing of the application, now you don't have to worry about breaking 100 different things because they're all together somehow. Instead, now you're touching one small microservice. It's much more controlled. Risk is controlled. And you want to do continuous integration and in the continuous delivery. We're going to get into that in the next slide. So the continuous integration essentially means that you have different people working on different parts of the application. You want that to be integrated continuously in automated fashion. So you have a system that's set up to run your unit tests, you know, your acceptance tests continuously. And then you have continuous delivery. Now that concept is basically the example you saw previously, the deployment pipeline. From the developer checking in the code, and it goes through an automated pipeline that can go all the way to production with some, you know, gates and checks in the middle. Some of them are automated, some of them can be manual, depending on the needs of the organization. So that is a continuous delivery, and you know, you could potentially, if a customer now has an issue, and then you can fix something and get this out the door very, very fast. Now, recently, Zoom had an outage. They fixed it pretty quick. Now, I don't know if it was an issue with the code or it was a configuration with the production, operations aspect of your infrastructure, whatever it is, usually is in the form of code, and they were able to fix it and then get that pushed out to production for the customers in a matter of hours. And so that's the advantage of that. And then self-service. Anyone has worked in an organization that has some kind of a traditional, separated dev and ops culture. If a developer wants something, say, oh, I got new software, I need to put this on a server, and they create a ticket, and then the operations will get to it, in a couple of weeks, for something really simple, right? And so, that is not, that's the opposite of a self-service. Self-service says, well, I provide you the tool. It's automated. You go change this through some kind of a, app, and then you can just adjust this by yourself. That's self-service. Containerization. Well, if you heard of a Docker, and of course, Docker is not the only solution for containerization. Containerization, the concept of that is you bring your own dependencies for your piece of software, and then you put that in a lightweight container, just like the containers on a ship. I mean, that's what they got the analogy. You have this lightweight container running. You got your own separate dependencies. You don't have to worry about what else is on your server. And it provides a lot of advantages. Is when you want to upgrade a piece of software on the operating system, you're not touching everything that's on the server. So you can basically just upgrade your container alone. Say, okay, now my application depends on this particular library, and now I need to upgrade it. So that's not built into your software, but it's kind of a underlying infrastructure level piece of software, and that can be upgraded on the container itself. So there's a lot to containers and why is it advantageous. It also allows easy testing, simulating your environment. So that's another good thing to do in DevOps. Monitoring and alerting. Monitoring and alerting, this is a huge for, when you run something in production, you need to keep monitoring the software. And are they responding quickly enough? If they are not responding quickly enough, perhaps an alert would be raised, and certain engineers would be involved immediately to look into the issue. Infrastructure as a code. So the computing platform maybe is on the cloud, and the networking and the configuration, those things in the old days, they were done semi-manually, and it was kind of fragile. You may go to a host, somebody just manually changes something, a configuration, and then it cannot be repeated. And if something goes break and you don't know what's going on. So now we said, we want to audit, we want to, make sure the code can be, the whatever change that was made to the infrastructure, it's treated just like the product, the software itself, that needs to be treated, the same way. So they are written in code and it's automated, and you check that in, your infrastructure gets updated through another pipeline. Except now you're not releasing the product that's gonna impact the customers. So this is something that's underneath that product for the infrastructure. So it's the same thing. It's the infrastructure as a code. And when you push some change to production, you don't want to introduce a downtime. So it's what's a popular word here is called the zero downtime deployment. That is kind of the standard thing. Say, well, if possible, this is what we're shooting for. Make sure that we'll make a change to our software is, or maybe infrastructure. We're not gonna, disrupt the service so that the user cannot access it. So that's that. So the CI, continuous integration or delivery, and that's usually shortened as CI/CD. And CI/CD is, you can say, is a hallmark of DevOps. And here is just another sample pipeline here, not too different from what the other one you saw before. You have code, and code checks in, and then it gets compiled and unit tested, and also functionally tested. This usually just runs locally. And then once you get the code pushed into the remote repository, then system will actually get the code deployed on some kind of build machine, or not deployed, just basically, running in a different machine. It's not your local, but this is not the eventual machine the way it's gonna run, so the other people can rely on for the service. But this is where you have a build infrastructure where it's automated to run tests with the software running on the build machine. And then you may also have that deployed to just the next step. It's all automated, and one after another, if it passes the tests, and it goes to the next. And then in the integration environment, and then you have some other suite of tests that runs, and maybe now you're integrating between this service with a bunch of other services to make sure that a larger function is performed correctly. And then you may end up deploying that after that passes that, and it goes to a so-called a UAT environment, a user acceptance testing environment, where potentially some end users, even if you want, can be invited to test in that environment. And that, if not, then you'll have your product owner, right? You're somebody that's the customer representative to verify that function works. And then you may, before you go to production, you may want to verify, okay, well, it's not just about functional correctness, but does it perform well? Can it handle the load? So you may also do performance testing in a separate environment. So now this is just an example. In reality, you can have various kinds of variations, but this gets you the gist of what CI/CD does. Now, another thing that person mentioned about zero downtime deployment, and one of the key idea behind that is a so-called blue-green deployment. You have a software, let's say currently is running in production. That's the green version of it. The green version of it, it has, let's say we have 3 layers. We have a web server, we have an application server, we have a database. Now, a user request comes in. Let's say we have another version that comes out, and you want to switch to it, right? You have this thing is serving live traffic. So you have some kind of software router that's routing the user request to the current production version. Now you have another candidate version that's to be released. You have that already running in the production servers. They may or may not be on the same servers. If they're in in containers, they could be in different servers, but conceptually they're in the same place. And then what it can do is, and then at one point, you say, let's switch to this version. So, well, before you switch, probably you have a mechanism to verify this actually works. But then let's say it's verified, and now you want to switch. So you just simply switch through that software router and configuration, and now it will direct traffic to your new version. So that's kind of the concept between, blue, green. You have a live version, you have another version that's, to be released, and then you just do that swap. The traffic is, shifted 100% from the current production to 100% to the new version. So that's pretty much it for what I would like to cover today. There's a lot more. If you're interested, you can look at this reference list and read them on your own. Thank you.